Right, this is Piers at Jersey Laser Scanning. This is a video where I've been trying to put out this video for months, but just haven't found the time until now. And this is to demonstrate the inspection quality level of detail. It's just the beginning of the capabilities available here. But first, let me go through this logically. What hardware was used, and potentially software. The computer-aided design software I use to properly check qualities of point clouds and things like that is Revit 2022. Agisoft Metashape Pro is the photogrammetry software you can see on the screen at the moment, which is takes the photographs, overlapping photographs, and allows the generation of a point cloud. And a point cloud is a cloud of point measurements. I use the drone used was a DJI Mavic3E Enterprise. The Enterprise bit's important. And on that drone, I also had RTK enabled with the RTK puck, which fits on top. Also, I use the MLID RS2 GNSS GPS receivers, one as a base station, one on a staff in order to check ground control points, but the same base station is what's feeding the information to the drone to enable each photograph to be accurate to within approximately 1 centimeter location-wise, which will assist the photogrammetry process. So just looking at the types of things I'm going to cover in this video, we have Agisoft Metashape Pro in here, and without going into too much detail here, there are two chunks as it's referred to in Metashape. One is the standard output, standard flight, and the other is chunk 2, which is the inspection quality level of detail, as I'm going to call it. We also have a comparison video, a side-by-side video, enabling there's ways of planning a virtual flight around the object, and I've taken that exact same path and done it for both models, so you can see the differences between the two. I've also got a small phone clip which I'm going to try and put inside this video. This won't be an extremely well edited video. It's not what I do, but it's going to be good enough for demonstration purposes. But that phone video shows how the drone moves when it's in this new flight plan method. It looks like something out of Terminator. I think it's hilarious, but also slightly scary at the same time, intimidating wise. So what else have we got? We've got the orthomosaics that are output. An orthomosaics just like Google Maps or Google Earth satellite view, but of course you're taking the images from much closer to the surface, so you're going to get much higher quality satellite imagery. So we're going to compare the orthomosaics from the two different outputs. And what else? And we're going to go into Revit and compare the two point clouds and orthomosaics for density, accuracy, and quality. So what is the aim of this video? I wanted to give you all the background to it first, and the aim of the video will be in the title to a degree when I upload it to YouTube. But it all started with me wanting to experiment and demonstrate the Agisoft Metashape Pro's ability to create its own flight plan, and for one to stipulate how far away it's going to fly from the object and things like that, and how that compares to what would be a normal flight, which I will describe and demonstrate here. It's important to thank some people for the ability to do this video, as anyone who does drone work and requires a work permit and things like that, they'll know that you've got to jump through a number of hoops and get permissions and make sure everyone's comfortable. And so I'd like to thank Jersey Heritage and the people there who enabled me to use this object as the object of the demonstration. This tower, Archirondel, I'm not sure if it's a Martello tower or a Conway tower. There are two types in Jersey. However, it is possible for guests to stay in these due to the Jersey Heritage work in preparing them in that way. Also, as a result, I'd like to thank the guests who were staying there at the time for allowing us to carry out these flights, which were done on 2 consecutive days. So grateful to them. I'm also grateful to a colleague of mine, Benjamin, who edited the video in a number of places, not the final output, but you'll see the parts where we have the comparison videos rotating next to each other. I'd like to thank him for his ability to do that, and also give him a quick plug for Two Wheels Feels, and he works on TikTok predominantly, but he's a motorcycle journalist, so covers all manner of motorcycles, which is also one of my passions. Archirondel cafe owners, and also to Alexander, my Project Trident student who worked with Jersey Laser Scanning on this, and created some very useful output and insight into things for the ability to carry out this properly. So what am I going to show you through the course of this video? I'm going to show you the standard method of using, in my case, DJI Mavic3E Enterprise 3D flight plan through Agisoft Metashape Pro. I'm going to show you the inspection quality method and how it differs, and that's basically it. I'm going to show you a video clip of Terminator drone doing its stuff. Obviously the reference Terminator is from the movie, and a comparison video of the visual output, and then we're going to look at the Revit interrogation of the standard and inspection quality point clouds, and also Revit with reference to the orthomosaics. Anyway, that's the preamble, and that took quite a long time, but it's important to get it all up front. If you are still watching, let's crack on. And apologies, I'm going to make sure I stick to that plan by referring to my notes. So, standard method. This is Agisoft Metashape Pro. This is the 3D point cloud tiled model, actually, I think. So I'm just going to double check on that. Let's have a look at the point cloud. So this is the point cloud generated by flying. I'm going to describe it as a crosshatch mission flight plan, and the quality is outstanding. The accuracy is very good, very, very good, sub-centimeter because of the height we flew and how much we overlap the photographs. And I'm going to show you the location of the camera points, so you can get a pretty good idea. So effectively there was flying directly overhead, so let's just go directly overhead. We're looking in orthographic view, so there's no perspective. There was a flight over the top where if you look at my mouse, it was looking directly down. That's called nadir. Sorry about these alerts in the background, but it's called a nadir perspective, where you're looking directly down. So that's the satellite photography side of things, you know, the equivalent. And then the other things you do on a standard 3-dimensional oblique flight is from one side it tracks back and forth to one side of the tower, looking at 45 degrees camera angle, so you can see the camera angles facing down that way, and it's capturing all the detail down here. And then it does it from the other side, and then goes 90 degrees, and from this side and that side. So that's how that was generated. It generated a 3D model in you know, the highest settings, probably a little too high for what it was designed for, the ultra high quality setting, and we have a point cloud of 27 million, almost 28 million measurements. And if I zoom in, you can see the dots beginning to dissipate, because each one of those is a pinpoint measurement, because it's matched pixels from from two or more photos, and triangulated that particular position in 3D space, and then colorized it with the photography. So those dots are red because that object was red at that point. So this is the output. What I'm going to do is describe to you that after we flew this, this would be the normal output. But to go to inspection and quality level of detail, we then wanted to experiment with chunk 2, which is you take this, you create a mesh, 3D triangulated mesh, and then you ask Agisoft to create a flight plan. And you put some details in about how far away you want it to fly from the object that you are outlining, and how much overlap and things like that. So the first standard flight was 372 images, and let's have a look at the tiled model on the standard one as well. Tiled model is a photorealistic equivalent of the point cloud, which uses the the photography from the drone overlaid onto a 3D triangulated mesh, and it makes something which is visually much more appealing, albeit not quite as accurate, and it means there are sort of slight bulges and things like that, but it is a very attractive output, and you can see the sort of level of detail. And sorry, that was me zooming in and cutting out part of the model. However, that is the standard flight, so I'm just going to minimize that, and now we're going to look at the equivalent of the other model. So this is the point cloud that was generated with this flight plan, which you can see how I set it up. I asked it to fly, I cannot remember exactly, it was the first time we did it, so we didn't want to go too close, X number of meters away from the object, and you can see the way that this automated flight plan that works with the Pilot 2 app I think I've got on the DJI Mavic3E Enterprise, and we plugged it in, held our breath, triple checked everything, and then pressed the button, and it was spectacular. And it did what was required. The output comparison is that instead of 372 images, it took 547, of course much closer, and the point cloud, instead of being in the standard method 28 million measurements, was chunk 2, let's go down to here, 303 million measurements. Okay, I'll let that speak for itself. So let me take away the camera positions, and you can see what I would describe as achingly attractive and accurate detail of each granite block and things like that. This is the point cloud, so this is just dots. So we're going to go to the tiled model now. You can see the accuracy. It believes it's got 1.54 millimeters per pixel. It's covered per pixel, and this is the visual output. Everything is just much more crisp. You can get to see the level of detail and the types of things going on in the relevant gaps. Have it go back. I mean, personally, I prefer the point cloud because I work in Revit, and Revit works with point clouds, and I can get what I need from that much more readily. hey, and it's up for debate which one is the one which would be most appropriate depending on the use case. I would suggest that this is excellent for visual inspection of areas that are hard to reach without having to put a person on a rope or create a structure around it, scaffolding, etc. And that's that output. Right, let me refer to my notes. I want to show you the video clip of the drone. So I'm going to show it to you on screen here. So as you can hear, it's taking multiple photos from each point, depending on what was most efficient for it. So that was that. I'm going to save the comparison video, and I will slide that in to the final editing, fade to black, just slip it in so you can see it. But that will go in at this point. So hello, welcome to the second part of this video showing inspection level quality versus standard oblique photogrammetry quality. I apologize for the difference in time between recording the first part and the second part. It won't make any difference to you because you're watching this all in one go. But if you notice on the bottom right hand side of the desktop screen, it's just over a week later. We had some time sensitive tasks which we needed to carry out. So having reviewed the first part of this video again, I've just made a quick list of things that I want to make sure that I cover off in this Revit part of the video, which is, what is Revit? Revit is a computer-aided design software used for surveys and creating items in the proper level of detail required if you're manufacturing or doing architecture, that sort of thing. And it's essentially the younger version of AutoCAD. It's also optimized for use with point clouds and various other things. But this is what we use at Jersey Laser Scanning as part of our core business when we do survey output. Why am I using Revit when you've already seen the photogrammetry side of things? Well, Revit's going to allow us to inspect the point clouds relative to one another, because we have essentially two different surveys done on 2 different days, and we want to see consistency, because that will represent the GPS consistency, but also the point clouds generated from one day relative to the other day, similarities and differences. We also want to see the accuracy or tightness of the spread of the points, representing the walls and things that have been measured, and how they differ. So we've got the orthomosaics, which I'm going to show you, and the difference between the two. And whenever we look at point clouds in here, because we've got 2 different point clouds, if we look at it in the colors that are in this sort of screen, if we had 2 surveys in what's referred to as RGB, or red, green, blue, or a normal camera like you have on your phones, it would be very difficult to tell the difference between the 2. So what I've done is, in the right hand side of the screen, you can see blue and green. The blue represents the standard oblique flights, which was the flying at 25, 30, 35 meters above the object, pointing at 45 degrees in various directions as well as directly down. And the green represents the Terminator inspection level quality of, or inspection quality level of detail available. So let's have a look at the orthomosaics first. So I've tried to line these up as much as I could within this part of the screen. We overlay orthomosaics quite often on to site plan or floor plan surveys or plan view surveys, because it embellishes the survey a lot, being able to see what's actually there, as well as having the contour lines and various things underneath the PDF photography as well. So this is the quality of output from the standard flight, and this is the quality of output orthomosaic from the inspection quality level of detail. So you can see that the lighting conditions were different on the 2 days. The sun is obviously low in the horizon, and that probably helps, because better light improves the quality of the photography input as well as output. But shadows can sometimes create problems, but in this case it wasn't a problem, and most of the information was regenerated very well. But if I start zooming in, the 2 are going to look slightly different, but you can see that the moss and lichen on the top here relative to the moss and lichen on this part, because it was taken so much closer, you can see that the details are popping out. So that's an orthomosaic, and it can be done from any angle. And like I said, it's I think I said it in this video, I re-recorded it a couple of times. The orthomosaics are 2-dimensional images, just like Google Earth satellite views, but they can be done from any angle, so you can do it from the side as well, should that be a desirable output. But so those are the orthomosaics. What else are we going to look at? The point clouds themselves. So now I'm going to put it on the plan view, but with the 2 point clouds represented directly from above. There are blue and green, and it looks messy initially, but then when we zoom in, things will become clear. So this is the 2 point clouds, or this is the image of the 2 point clouds overlaid against one another. And if I zoom in, you can see one versus the other, and the lines up here. But it's not desperately clear, because you've got 2 sets of images with overlaid points fighting against one another, but it's representative. I think probably what's best is if we look at the right hand side here of the screen, and these because Revit works quite well. I'm going to move across to this complex or the inspection level quality. We've got two section views here. We've got the cross section view, which is looking this way, which represents this screen. And we've got another section here looking this way, which is the long section, which is the lower part of the screen. So all I'm going to do is move this further back, and you'll notice the top side of the screen changes. And then as I move that section through this way, we can look at how the point clouds compare to one another. So moving live, you can see it on the left screen, moving that direction. You can see it on this screen, moving from right to left, and it's essentially looking to the north because this is geo-referenced. So let's have a look as I just move through here. So green represents the new or the more inspection quality level, and let's just move through slowly through the item here. Now each of these sections are 3 centimeters thick. So this is only 3 centimeters thick. If I zoom in, you can see that's actually 3 centimeters in depth. We can change that to be whatever we want, and what I will do is change that to 1 centimeter there, and I will change the same to this one, so we can look at it in its highest possible detail, and we'll keep moving through here. And you can see that yes, they match off against each other, which is really good and nice to see, and it shows consistency, which consistency is ideal because if you're measuring the same item over long periods, should we say you do one on year 1, one on year 2, one on year 3, you can compare these point clouds against one another. One can do it visually like this, or you can allow me to do some cloud comparison analysis, which would create a single point cloud output which changes colors depending on how far one point cloud is relative to another, and you can change those distances and the heat colors, but it creates a very quick visual representation of whether anything has moved. So let's continue moving through this. As we get to the tower element here, you'll see that the tower is split and separated out, and as we get to the tower proper, when I say tower proper, we're moving through to the maximum diameter area. We can see that if I zoom right in, hopefully this is coming out in the right sort of quality, you can see that the blue dots are quite sparse because of the 1 centimeter of depth we're looking at relative to the green. The green is obviously much thicker because we've got significantly more, a large number of points. I think from memory there were about 28 million points in the original point cloud, and over I think about 300 million points in the inspection quality level of point cloud. But I am happy with that level of detail, the consistency and the accuracy of those points, and obviously the density. So let's have a look at this one again from this perspective. So what I'm going to do is move this section cut, which is this one here. So I'm going to move this one through the Conway Tower. And we can see how the spread of points differs, and the thickness and the consistency. So I mean, this is a pretty sharp and accurate point cloud survey derived from photogrammetry. We have LiDAR units as well, ground-based and airborne-based, but you can see that getting in between the cracks and so on, we've got that sort of level of detail. So I'm pretty happy with that as far as being able to interrogate it and maybe generate that sort of heat map output, should we want to do one versus the other. So there's not much more to add on that other than we are looking at it in a computer-aided design program, which will enable us to properly inspect it rather than look at what are just pretty pictures in the photogrammetry software. If you pull it into a computer-aided design program, you can scratch the surface a bit deeper and have a look at the detail, and hopefully that was of use. But I hope this video in its entirety was useful, and thank you very much. Bye bye.